Right. So we are talking about, I just remind you, the context. Okay. So what we do, oh, by the way, one thing. I think you have all been notified that you have just been graded for your assignment, right?
I didn't get the chance to check, but I will. So.
Oh, okay, but the thing, well, Moodle tells me he's going to send you some notification. Didn't you get an email or something like that?
I'm not sure I have my mail synced on
Oh,
the
okay.
phone.
Okay.
I will have to check that also.
I see. Okay. Are you driving again?
Maybe.
I'm not the police, you can tell me. And even if they watch this, since they didn't catch you in the act, it's moot.
Yeah. Okay.
Okay.
I get still here, so you
The
have
only
my full attention.
the only thing I'm going to ask you is to keep your eyes on the road and not on the
Yes.
screen,
Yes.
because it's going to be recorded anyway, so you can just listen to us.
Yep.
Okay?
I know that from previous sections.
Okay, fine. I'm glad you see it this way. Okay. Where were we? Okay, so we were talking about second order systems. We are going to make it short tonight because if it's only the two of us or the three of us, I think we are just going to sketch some ideas. Maybe I'll try to show you something in MATLAB or Maple, and then you've got new material set up on Moodle. Actually, I'm going to show you this. I'm showing you Moodle once again because I think it's quite relevant. So I'm opening Moodle. Okay, I'm logging in. Okay, I keep logging. I'm in. So this is the course. Okay, so we are looking now at the week November 9th, November 15th. You can see here I've got a very short, actually a one-page lab lab material, lab lecture, lab seminar. Okay, uh, it's about equilibria for second order systems. You can see here it's got two problems actually. Okay, it's telling you how to fix these things. Okay, and actually I think I'm going to make this your assignment because it's quite interesting. This can easily be your assignment. And then you've got a folder built up here with a few things. There is a small a small file called home1 with a couple of nice exercises about second order systems and a bunch of Maple worksheets with some exercises from some French book where you have given some systems, and you can see we are computing the equilibria and we are computing the phase plane, and we are watching something nice about it. Maybe I can show you some of these files myself. Okay? Okay. So let's go back to the week. And this is going to be your assignment. It's been prepared here. Okay? So you've got enough material to start studying about the things we are talking here. Okay? Okay, let me go exit Moodle, go back to my notebook. So we are talking about nonlinear systems of this form. Okay, x dot is f1 x dot x and f2 of x. So this is f of x, where x is x1, x2, which belongs to R2. Okay. F is smooth. Okay. F is smooth, so it's easy to discuss things. Okay. And of course, if we are going to check the equilibria, this is equal to fx This is equivalent to fx is 0, which is equivalent to f1x is 0, and f2x is 0. And then you get an equilibrium point x star, which is x1 star, x2 star, which again is part of R2, is a vector from R2. Okay? So this is the context we are talking about. Okay? So x, right? X equal x1 or x of t, if you want to be accurate. So x of t is actually x1 of t and x2 of t. And these are trajectories. These are trajectories. The trajectories are essentially in the plane x2 versus x1. These are the trajectories. Okay? And somewhere we've got equilibrium. Okay? We've got equilibrium points where f of x is 0. Equilibrium points, okay? Where the derivative is 0. So you've got constants. Okay? You've got constants. Right? We have to understand what happens and what is actually the behavior around these equilibrium points. What is the behavior of these equilibrium points? So we are going to plot, for all of this, we are going to plot, we are going to have 3 plots in general. 3 plots. Okay? So it's going to be x1 versus time, x2 versus time, and of course, the most important of them, to understand the full behavior of the system, x2 versus x1, the so-called phasor or phase plane. Okay, these are the 3 graphs. For instance, example, if we are talking about the pendulum, so it's the equations for the pendulum are z double dot, let's use z, or y double dot, okay, plus sine y times some coefficient, okay, plus y dot equals 0, okay. This is in general the pendulum. This is a pendulum equation. Okay, this is a pendulum equation. Okay, so this is equivalent. This is equivalent to x1 dot equals x2. x1 is the position, angular position actually. Yeah, is the angle. Let's call it angle. And x2 is the velocity, the rotation velocity, okay? Because it's a rotation movement. And x2 dot is minus sine of x1 minus x2, okay? So f of x is x2 and minus sine x1 minus x2. This is your f, okay? And the equilibrium points are x star is kp 0, okay? It's kp 0. It's kp 0. And if you look and you plot x1 versus the time, okay, you'll see damped oscillations. Similarly, x2 versus the time, probably you'll see some damped oscillations. And then the question is, but what is this plot? x2 versus x1. What is this plot? This is very interesting because we need to understand the trajectories in the state space. These graphs, these 2 graphs, don't show you anything. They just show you the time evolution, and they show you that probably they are stable. This is around. Of course, this is a behavior around x star is 2n plus 1 pi. So sorry, 2n pi. It's the even, right? The even stable, 2n pi 0 stable. Probably this is stable because they're all going to the same equilibrium, right? Or equivalently, it's the same thing to consider this the origin. So it's probably here. This is the behavior here. And somehow, we don't know how, the system, the trajectories are going to 0. What happens, however, if I initialize here? Right? So if I start from the initial conditions, yeah, these are x naught. How about if x naught is here? Where does it go? Where is it going? Is it going to the equilibrium, to the stable equilibrium, or is it going in a different direction? Or is it going to the other equilibrium? Okay, the other equilibrium, which is pi 0. Sorry, which is, no, this is not correct. Is it going to pi 0? This is pi. This is the other equilibrium. Is it going to this equilibrium? But how? I don't know if this equilibrium is stable. Maybe the trajectories fly away, run away from this equilibrium. Maybe they run away from this equilibrium. Question mark. What's going on here? So this is what this whole chapter is going to tell you. How the system behaves, how the trajectories we study geometry. We study the geometry of the trajectories. Of course, not only the geometry, using also, or taking into account, actually not using, but taking into account the direction of tracking the trajectory, okay? The direction along the trajectory. Do I make myself understood? Is it clear what I'm trying to tell you here?
Yes, it is.
So essentially, we are trying to understand the behavior because we don't know. We only know that probably in time it's going to behave like x1 versus t and x2 versus t, but this is not clear. So we are going to give certain conditions on and explanations on how the trajectories behave, near the equilibria. This is what we are going to study. And how are we going to study this? We are going to study this by judging the linearized system, which is a different object. I remind you, which is a different object. We are going to study the linearized system. X dot is AX, where A is a 2x2 real matrix of real numbers, and A is the Jacobian of F with respect to X, evaluated in the equilibrium point. So given by formula 12. This is A, okay? This is A, and we are going to study the eigenvalues of A, because A, the system with x dot is AX, has the only equilibrium point in the origin, in 0, and the behavior of the linear object in 0 gives us sufficient conditions, essentially, for the behavior of the nonlinear trajectories of the nonlinear system itself. How are we going to do that? Okay, So a matrix A has got eigenvalues, or poles, as we used to call them when we are talking about linear systems. In this case, we are talking about poles because we don't have a common poles and zeros, okay? We are going to talk about eigenvalues here, essentially. So we've got a matrix like this, okay? Like 13. And we are interested in the qualitative behavior of the system, okay? We know that the solution is the exponential of AT times the initial condition. We know that. This is very common. Okay. The only equilibrium point is 0. Okay. And we also know, and I showed you last time where this is coming from, we've got a simple characterization of the eigenvalues of a second order matrix, of a 2x2 matrix, okay? And this is given by this equation with a trace and the determinant as two parameters, okay? The trace is usually related to the sum of the eigenvalues. This comes from the relations of Viet applied to this second degree polynomial equation, okay? So the trace is the sum of the eigenvalues, whereas the determinant is the product of eigenvalues. Again, the Viet relations, okay? The Viet equalities, okay? So if we want to check the eigenvalues and their behavior, we need to use coordinate transformations, okay? To emphasize the presence of the eigenvalues of the matrix, okay? So we are going to use transformations like T, like this one, okay? And I showed you last time how you apply a coordinate transformation. You just substitute Z in this equation, and then you get that A hat is TAT inverse. T is usually an invertible matrix, otherwise it cannot be a coordinate transformation. And A is usually in a Jordan canonical form. Of course, depending on the type of eigenvalues, you've got different types of Jordan canonical form. And we've got here all the possible situations. We can have real simple or multiple eigenvalues, and then you get this type of matrix for diagonal, or this type of matrix for Jordan block. I would just put 1 here instead of the star, because it's usually we use 1. In general, we use 1. Or we can have complex conjugate eigenvalues, yeah, because we know that a second degree equation, okay, has either 2 real roots or 2 complex conjugated roots. This is the fundamental theorem of algebra. Yeah, the fundamental theorem of algebra is usually telling us that a polynomial equation of degree n has uniquely n possible roots. Okay, so since we've got only 2 possible roots, we can have either 2 real roots or 2 complex conjugated roots. There is no other possible way. Okay. For the complex conjugate eigenvalues, you can usually make a coordinate transformation of this form, making the matrix A hat looking like a rotation, with the real part of the eigenvalues on the main diagonal, and the imaginary part of the complex eigenvalue is on the skew diagonal with a sign change. Okay. So it's sigma on the main diagonal and omega and minus omega on the secondary or skew diagonal. Okay? Right. So these are the only possible 3 situations we have to study. Okay? Right. Then the solution of number 15, is this one. Okay? Is this again related to T, to X? Is this related to X? Well, we know that A, right, E exponential of A hat T, X naught, is exponential of t a t inverse x naught. But we know from matrix functions, right? So exponential e to the power m, where m is a matrix function, and we know from numerical methods that a matrix function, for a matrix function, we've got the following property. The coordinate transformation t jumps out of the, and t inverse as well, jumps in front and in the back, in the rear of the exponential. Why is that? Because we remember that the exponential emx is I plus mx plus half m square x square, right? This is the definition of the matrix exponential. Yeah, and if m is t m hat t inverse, then e to t m hat t inverse is I, again because this the function is 0, plus t m t inverse x plus t squared m squared t minus 2, plus and so on. Now, if you just take out a t, okay, okay, or this is equal if you just take out two factors, okay? So this is t inverse, this is I, plus t mx, actually m, okay, you can just take the common factors, okay? X is sorry, x is a real number, so x is commuting, so you say t mx t inverse plus t t mx t inverse plus so on. And if you take the common factor, this is essentially what? This is t e to mx m hat x hat, should have hat here, okay. M hat x t inverse. So the coordinate transformation jumps in front and in the rear of the matrix exponential. So this means that this is t e to the power a t inverse z0. This is x naught, okay? Okay, so it's actually related. It is related, yeah. So z is actually t x, okay, is tx, which is the coordinate transformation. So it's correct. They are related to one another. Both relations. So the solution of the equation z dot is a hat z is equivalent, or is just in different coordinates than the equation in x, and the coordinate is signified by the matrix T. So it's correct to do this. It's correct to look at the a hat system. So we don't need to judge, we don't need to study the A system, but we need to study the a hat system and then return to the A system using the coordinate transformation. Okay? Right, so now we study all the possible cases. All the possible cases. We have real eigenvalues. Real eigenvalues. We have real eigenvalues when the delta of the equation. Oh, sorry. When the delta of the equation. Where is it? Oh, where the delta of equation 14 when the delta of equation 14 is positive, so delta is here trace of a squared minus 4 determinant of a. You agree with it, yeah? Is the delta of a usual second degree polynomial equation. Well, when delta is positive, the characteristic equation 14 has two distinct real roots. E to the power lambda 1t z10, z10 is the initial condition for the first equation, and z2 is e to lambda 2t times z20, okay? Now, if we want to see the dependence between z1 and z2, okay, we can just easily write, we can just look at who is d2, okay? So how do we do this? So we have that z1 is e to the power lambda 1t z10, and z2 is e to lambda 2t z20. So from here, we have, from the first equation, we have to get the exponential. We have to compute this depending on z1. This is the trick. So e to lambda 1t is z1 to z10, okay? Okay. Right. So we need here, we need the e to the power t. We need the e to the power t, right? Okay. And here, how do we do this? E to the lambda 1t. Now you get that lambda 1t is ln natural logarithm z1 to z10. Then t is 1 over lambda 1 natural logarithm z1 to z10, which means t is what? Ln, t is ln, how? Is ln z1 to z10 to the power 1 over lambda. You agree? Do you agree? It's true. Huh?
Yes, yes, it is.
Then you multiply this with lambda 2. Lambda 2t is lambda 2 ln z1 z10, which is actually ln z1 to z10 to the power what? Lambda 2 over lambda 1, right? So that means if we go back to z2, this means that z2 is z1 over z10 to lambda 2 over lambda 1, lambda 2 over lambda 1 times some constant. This is the dependence of z2 from z1. Let's see. Oh, it's correct. Look. Okay. Of course, you get the constant replacing this, yeah, because z20, okay, you can get z20 from here, And once you replace this, you can easily compute the constant C like in 17. So, no, sorry. Actually, no, this is wrong. This is wrong. This is wrong. Let's write it clearly because they are right. I was trying to tell you that Z2 is Z1 to the power lambda 2 over lambda 1 times what? 1 over Z10 lambda 2 to lambda 1. Okay? Okay? Of course, times Z20. And this is the dependence. This is what Z2 looks like for Z1. Okay? Z2 depends on Z1. This is the dependence, relation 17. Yeah? This is what it is. Z2 depends on Z1. So now it's only fair to say what happens because the power of Z1 is rational exponent, okay, is a rational power. We have to discuss what happens. We have to discuss what happens when lambda 2 is higher than lambda 1 or lambda 1 is higher than lambda 2, and also what happens if, for instance, if they're both 0, or if 0 is between them, or if 0 is to the left. Okay, so we've got three cases. This is lambda 1, this is lambda 2. So we've got case 1, 0 is here. No, we have it differently. Okay, it's different. So we have lambda 2, lambda 1, and we've got 0 here, or we can have 0 here, or we can have 0 here. So we've got three situations. We've got three situations, right? Three cases, actually, not three situations, three cases. Got three cases. We've got three cases. And we are going to study the three cases, okay? So, first of all, if this is for the first case, so we are talking this situation, lambda 2, lambda 1, and 0, okay? So lambda 2 and lambda 1 are both negative. That means their product is positive, or their quotient, okay? Product or quotient, they are both positive, okay? Lambda 2 is smaller than lambda 1, so lambda 2 over lambda 1, lambda 2 over lambda 1 is less than 1. It's less than 1. So if this is less than 1, that means that Z2, okay, Z2 is going to 0, okay, when t goes to infinity, okay? T goes to infinity because of 16, you see? Look at the relation. Z1 is going to 0, Z2 are both going to 0. Z1 is also going to 0 when t goes to infinity, okay? But who goes faster? That's the question. Which one of them goes faster? Which one of them goes faster? Z1 or Z2? Which one is going faster?
Z2.
The one with the eigenvalue which is smaller, which is Z2. Of course, correct. Because lambda 2 is the smaller eigenvalue, the smaller eigenvalue. Yeah, the more negative eigenvalue, let's put it this way. that means that lambda 2 is faster. So lambda 1 is slow, lambda 2 is faster. That means that z2 is going to 0 faster than z1. Okay? Eigenvalues have directions, have eigenvectors, yeah? Need I remind you, I mean, I think I showed you last time what an eigenvalue is. So an eigenvalue has always got an eigenvector associated to it. So the eigenvectors are also slow for lambda 1 and fast for lambda 2. Okay? Fast for lambda 2. Okay? Also, we can define here a slope. The slope, yeah, the derivative of the function z2. So here we've got, just to make it clear, we have that z2 is a function, let's call it g, is a function g of z1. Now, we are looking at g prime. We are looking at g prime of z1. We are assessing this quantity. Okay. So the slope now is g prime of z1. This is called m. Okay, and this is what? If you take the derivative, lambda 2 over lambda 1 jumps in front. Okay, so it's constant times lambda 2 over lambda 1 times z1 to the power, whatever the power was, minus 1. Minus 1. Okay? Now, since lambda 2 and lambda 1, lambda 2 is smaller than lambda 1, I'm not sure this is correct. This is the other sign, right? You agree? This is like this. Because lambda 2 is faster, so is smaller. Lambda 2, lambda 1, 0. They have the same sign. This is less than 1. Okay? This is less than 1. So lambda 2 over lambda 1, lambda 2 over lambda 1 minus 1, this is negative, right? You agree? Because lambda 2 and lambda, they have the same sign. Okay, so the slope goes to 0. The slope goes to 0 when z1 is going to 0. When z1 is going to 0. And when z1 is going to infinity, z1 is going to infinity, this is going to what? This is going also to infinity, right? It doesn't matter that this is oh, but this is negative. This is negative. I think it's different. It's the other way around. You agree? Infinity is here and 0 is here. Because this is c lambda 2 over lambda 1, 1 over z1, right? 1 minus lambda 2 over lambda 1. You agree? Something like this. We'll check it anyway. That means for small z1, okay, the tangent, the arctangent of the slope, because the slope is the tangent, yeah, the arctangent is almost 0. That means we have trajectories which are tangent to the horizontal axis, and the slow eigenvector for large z1. So when the tangent is half pi, trajectories are parallel to the z2 axis. So it's kind of this situation, yeah. This is for large z1. So this is z1, this is z2. So for large z1, it's like this. And for small z1, it's like this. It's like this. Okay? Okay? So you can have either like this, you can go this way, or you can go this way. Okay? This way, or you can go this way. True? We are talking about the behavior of the linear system z dot. I remind you, z dot is a hat z, and 0 is the only equilibrium point. And we are looking at the behavior around 0. True? True. Okay. So such a type of behavior, tangent to the horizontal, close to 0, okay, and tangent to the vertical axis when it's close to, when z1 is quite large. Of course, essentially it's not only z1, but this is large z1. You see what I mean? Actually, we are talking about this, about large values of z1 in this form. Okay, so you can see here, okay, that you've got the directions given by the eigenvectors, the slow one and the fast one, slow one and the fast one. Okay, this configuration is called a node, and if the solution is going towards the equilibrium point, you've got a stable node. You've got a stable node. Okay. Note that z1 and z2 are invariant for the system 15. They are invariant. It doesn't matter how you change them, the behavior is the same. They correspond to the eigenspaces of the eigenvalues, and the eigenvalues are not affected by any change of coordinates. You know that. So that means that it doesn't matter that I've got my system like this, or I've got my system like this. The behavior is the same. It's just gonna get skewed by the direction of the eigenvectors. Here the direction of the eigenvectors are z1. I think I made a mistake here. These are not the eigenvectors, sorry. Here the eigenvectors are z1, are the directions, the axis of z1, and z2, that's the idea. Okay? Right. So we've got, this time, we've got here, we've got a node. This is called a node. Okay? This is called a node. And it looks like this. This is a node. You see? This is a node. Of course, if the node is stable, this is a stable node. This is a stable node. Whereas this is an unstable node. Yeah, because the trajectory is fly away or flee away, flee from the equilibrium point. This is the behavior around small variation of the small variations around the equilibrium point of the linear object. Okay, so this can be easily extended to the nonlinear object around its equilibrium point. So if you go back to the initial coordinate system with a T inverse, so this going back means using multiplication with T inverse. Okay. Of course, that the curves of the node are going to change their form, but not the topological character. So this is the same. This is the same. If it's a stable node, they just go to the stable equilibrium. Okay. So they don't lose their character. They don't lose their properties. they just change the shape. They just change the shape. Now v1 and v2 are the real eigenvectors, because we changed the coordinates, are the eigenvectors of the two eigenvalues lambda 1 and lambda 2. So this is how a stable node is looking in general. Okay, this is how a stable node is looking in general. Yeah? So this is x2 versus x1, whereas this one is z2 versus z1. Okay, now if lambda 1 is larger than lambda 2 is positive, so if the two eigenvalues 0, lambda 1, lambda 2, okay, the node is unstable. So if these are negative, if the eigenvalues are negative, we know that these two go to 0. These two go to 0 for lambda i negative. Whereas when they are positive, okay, in this case, then z1 equal e lambda 1 t z1 0 goes to infinity when t goes to infinity, and z2 equal e lambda 2 t z2 0 goes to infinity when t goes to infinity. So this is an unstable node, like I showed you. That was a stable node, whereas this is an unstable node. So this case here is lambda I less than 0. This is lambda I larger than 0. Okay, or actually I should write this in red ink. This ought to be written in red ink. Okay, right? Have you got any questions so far?
No question.
Okay. Right. Now, what happens if we've got eigenvalues of opposite sign? That means the determinant is negative. So it's this situation. What happens if we have this situation? Lambda 1, lambda 2, and 0 is in the middle. 0 is in the middle. Okay? So that means that z1 goes to 0. Goes to 0. And e to lambda 2t goes to infinity when t goes to infinity. Okay? So one goes one way, the other goes plus minus infinity, of course. The other one goes another way. Okay? All right? This type of behavior is, we call it a saddle point. A saddle point. Okay? Because it essentially looks like, I think I have a plot here somewhere. Okay, yeah, because I have a plot here. This is what a saddle point looks like. It never goes to the equilibrium. So what do you say? Is a saddle stable or unstable? Doesn't matter the direction. Is it a stable or an unstable? So this is for Z. Again, this is the same discussion. This is D2 versus Z1. Oh, it's written here. And this is X2 versus X1. What do you say? The saddle point, is it a stable point or an unstable point? What do you think?
Since we have a positive eigenvalue, I would say it is unstable.
Of course, it's unstable. No matter what happens, the saddle point forever or always Always unstable, of course. Very good. Very, very good. It's true. Now, what happens when you've got a real eigenvalue of multiplicity 2? Okay, so lambda 1 is lambda 2 is lambda of multiplicity 2. Then the Jordan form is a Jordan cell. It's called a Jordan cell. Okay, so you have two situations: the Jordan cell itself, or we call this one a degenerate situation, because you can never have a coordinate transformation that is bringing your system into such coordinates. Okay, this is just a so-called degenerate situation. Okay, a degenerate situation, and things can be done in the same way. Now, in this case, if lambda 2 equals lambda 1, you've got z1 dot is lambda z1 plus z2, right? And z2 dot is lambda z2. Then we know that z2 is e to the power lambda t z2 0. So we substitute it in the first equation. So this is lambda z1 plus e to the power t lambda t z2 0. Okay, or what we can do is actually get lambda. So lambda here, lambda t is ln z2 0, correct? Correct. Okay, so that means lambda is 1 over t ln z2 0. So that means that then we can write that z1 dot is lambda, which is 1 over t ln z2 0. This is z2 0, right? Plus exponential, or we can just write this. Well, leave it like this. T, or we can just times z1 times z1. This is a bit more complicated, you see. Times z1 plus what? E to the lambda t, so that means exponential lambda t was this, so this is z2 over z2 0 times z2 0, so this is z2 actually, right? Of course it's z2, that's true. Okay, so z1 dot is this one, z1 dot is this one. Okay, this is z1 dot, and from this one you can just get the solution. Okay, you can just get the solution. But why do I have z1? Because lambda z1, okay. I got lambda. This is a bit more complicated, right? But but it can be easily written. You can easily write Z2. Okay. Oh, I'm making a mistake here because this should not be so difficult. Of course, you can also study yourself this weird case, but this is simple. The second case is simple. So Z1 dot is lambda Z1, Z2 dot is lambda Z2. Okay, so this means that this means what? This means that Z1 is e to lambda t Z1 0, and Z dot is e to the power lambda t times Z2 0. And this is this e to the lambda t is Z1 over Z1 0. So that means that Z2 is Z1 over Z1 0 times Z2 0. So this is just a piece of line. This is just a piece of line. So that means that Z2 is Z2 0 over Z1 0 times Z1. So it's essentially Z2 over Z1. You've got this. It's this. It's a straight line. So the degenerate case is a straight line. Agreed? This is the degenerate case. Now, if lambda is negative, then you have this. And if lambda is positive, then you have the other way around. But I'm going back to the Jordan cell case. I'm going back to the Jordan cell case because this, I don't understand why I find it so difficult to find the relation. So you've got Z1 dot is lambda Z1 plus this one. Okay. What am I doing wrong here? What am I doing wrong here? Lambda Z1 plus Z2. Okay, and lambda Z2 can be computed. Then you substitute it back. And what? Well, you can do this. Just substitute this. I'm doing something wrong. I don't understand what. I don't understand what. Just hold on a second. I'm gonna check something. I'm just going to check something. I have a notebook here. Yeah, I found the proof in a notebook of mine. So what you can do, you just get T, you just extract T just like I did here. Then if you want to sort it out, oh, yeah, it's a bit more difficult. It's a bit more difficult. But I'm going to show you, I'm going to send you the proof. I'm going to make a photo and send you the proof, because this is a bit more difficult. What you can actually do here, you can use the classic Laplace transform. You can use the classic Laplace transform, okay, and compute this, right? And then you can just extract from one the other one, which has a bit more difficult relation, okay? And what you get here is a plot, something like this. You have some interesting curves, something like this, for instance, okay, or something like this, right? So this is the case lambda 1, lambda 1 0 lambda, okay? The proof is a bit more. The proof is a bit more involved. It takes a little bit longer, but essentially we extract T. Or lambda T, but T is enough. Then you can just, oh, this is e to the power lambda T. I don't know what T is doing here any longer. Okay, so this is one mistake I made. Okay, so you've got this. This is an equation in Z1 and Z2. Okay, this is an equation in Z1 and Z2. And actually, you can write that Z2, right, is Z1 dot minus ln Z2. It shouldn't be Z2 here. Or something like that. Z2 0 Z1. Okay. Ah, but this, we know we have this one. We have this one. Right? So T. Okay. Right. Like I said, the proof is a bit more involved. You can use also the Laplace transform to start computing this. And then you end up with a more complicated shape of Z2 as a function of Z1. It's a bit more complicated. Okay. And you can just plot it. I can show you, I can give you the relation, and then you can deduce it if you like. So I think it's Z1 versus Z2. I computed here. It's Z1 versus Z2 I computed here. So Z1 is Z2 times Z1 naught over Z2 naught minus 1 over lambda ln Z2 0 plus 1 over lambda ln Z2. Yeah, it's a bit more complicated. But it can be done, and you can find it in books as well. So these are the situations when you've got real eigenvalues. When you've got real eigenvalues, I'm just going to make, gonna write up a conclusion here. Okay. So real, or the linearized system, the linearized system has real eigenvalues, okay, then we've got several situations, okay. 1, lambda 1 smaller than lambda 2. This is a stable node. Okay. 2, this one. Oh, sorry. Even if lambda 1 is less than lambda 2. Okay, make it like this. Let's just write it like this. Lambda 2 smaller than lambda 1. Okay. If this is the case, then you have an unstable node. It's this one. Okay. Then you've got the situation here. We've got the situation, let's call it 1a. Okay. Lambda less than 0. And here you've got, or you can call it situation 3. You can call it situation 3. And you've got 3a, like this. The one I couldn't prove very easily. Okay. And then you've got 3b. You've got the lines. Okay. This is in canonical coordinates. Okay, because then if you go back to your real coordinates, they are just going to get skewed. Okay, they're just going to get skewed. Of course, number 4, you've got lambda positive, 4a. Okay. For B, oh, sorry, for B, no, sorry, I was wrong again, because you need to go away from the equilibrium. Okay, these are the situations for real eigenvalues. Okay, these are the situations for real eigenvalues. Right. Now, that's the behavior of your system around the origin for that kind of eigenvalues. Okay. Now, if we are going to talk about complex eigenvalues, that means the delta of the equation. This is delta. The delta of the second order characteristic equation is negative. Then you've got 2 eigenvalues which are complex conjugate. Okay. That means that the trace is twice the real part, and the determinant is nothing else than the what? What is this? These are lambda. What is this? What is this? If this is lambda 1 and lambda 2, what is this? The product is lambda 1 times lambda 2, or It's this. True. It's the absolute value of one of them. It's the absolute value of one of them. You agree? I guess so. Okay. So in canonical form, we've got this A hat. And then the equations in the canonical forms are Z1 is sigma Z1 minus omega Z2, and Z2 dot are omega Z1 plus sigma Z2. Okay? Right? How do we compute this? This is no longer possible to do with the simple calculations because you've got a full nonlinear system. Then we use something which nonlinear people use quite a lot. We are using the so-called nonlinear, the so-called polar coordinates. So you go to polar from Cartesian, these are Cartesian coordinates. Cartesian. You go to polar coordinates. You go to polar coordinates using this relation. This is the polar. This is the polar coordinate transformation. Z1 is r cos theta. Z2 is r sin theta. These are polar coordinates. Okay, where r is the absolute value. This is absolute value squared here. Sorry. Where this is the absolute value. Okay. Of a complex number. Okay, so this is it's actually the radius. It's the radius in polar coordinates. Okay, because polar coordinates are essentially about a circle. Okay, so the movement is happening in this circle. This circle is radius r, and theta is the angle, because the things. So if things are moving in the Cartesian like this, here in the polar coordinates, things are moving on this circle. Okay? Do you understand what I'm saying? Does it make sense?
Yes, it does.
I think it does, because this is polar coordinates. We go from Cartesian to polar coordinates. Okay? And of course, the angle is always the arctangent between Z2 and Z1. Okay? Then, of course, automatically the initial conditions are R0, which is R of 0, which is this one. And of course, these are, I forgot to mention, these are circles like this, yeah, because R depends on time. R depends on time. Okay? And there are points here. Okay? And once you apply these coordinate transformations, you get the so-called decoupled system, which is r dot is sigma r, and sigma is the real part of the eigenvalue, and theta dot is omega. Theta dot is omega, a constant, the imaginary part of your eigenvalue. And the general solution, of course, for the first equation is very easy. Is R0 exponential of sigma t. And now you see when sigma is negative, R is going to 0. So when sigma is negative, you go like this. The R goes like this. And when sigma is positive, the R goes like this. Okay? So this is for negative sigma. This is for positive sigma. Okay. And of course, what's its name? The angle is just a first order degree function, polynomial function. Okay, is a linear function in theta. So it's omega in t. Sorry, in time t. It's omega t plus theta 0. Okay, eliminating. Eliminating the time variable t from these equalities. Okay, so you just take t equal theta over theta 0 over all times 1 over omega. Of course, you can just substitute this in this equation, and then you get this relation number 18, r of theta. So r depending on theta, r depending on theta. Okay, so how does the radius depend on angle? Exponentially. It depends on the angle exponentially. Okay, so the curve denoted by 18 is also called logarithmic spiral. Logarithmic spiral, and the corresponding equilibrium is called a focus, because what happens, it's something like this. Okay, this is what happens. This is what happens. Okay, so coming back to the Cartesian coordinates, because this is in polar coordinates. Coming back to the Cartesian coordinates, you know that the general solution this time is, because what we have is z1 is r cos theta, so z1 is r0 e to the power sigma t, okay, times cos omega t plus theta 0. So you just replace, once again, you have r and you have the sine, okay, and you have them here, okay, you have them here, you just replace them, you put them back, you get this form, and then you get this kind of behavior, the focus behavior. Get the focus behavior, okay, stable focus and unstable focus. Okay, stable focus when the sigma is okay, when the sigma is negative, then you get stable focus, and when the sigma is positive, you get unstable focus. You get unstable focus. Okay. Okay. Does it make sense? So it's a very nice behavior when you've got complex conjugate values. You've got complex conjugate values. We have other special cases. Okay. I just said that if sigma is negative, that means the trace of A is negative, then you have stability. So the focus is stable. If the trace is positive, that means the real part of the eigenvalues is positive. Okay, then the sense of the motion on that curve is reversed, and then you have an unstable focus. Now, what happens if your eigenvalues are on the imaginary axis? What happens if these are your eigenvalues? What happens in this case? That means that the trace is 0. That means that A has pure, okay, that I just said that means A has purely imaginary axis. And then, okay, then you substitute this, because the sigma is 0. You substitute this becomes 1. And then you've got the cosine and the sine, okay, times constant, okay, times constant. So the trajectories will actually stay on what? They are going to stay on the trigonometric circle. You agree? Do you agree?
Yeah.
They are going to stay on the trigonometric circle because one is sine and the other one is cosine. They both have the same radius, and they are going to stay there with the radius r0. With the radius r0, because the radius is constant now. The radius is constant now. So that's called a center, and it looks like this. That's called a center. Unfortunately, if you get such a behavior, can you tell me if the system is stable or unstable? If the behavior around the origin is of this type, how can you tell if the equilibrium is stable, whether the equilibrium is stable or unstable? How can you do that?
It's neither.
It's neither.
It will be attracted to that center.
Exactly. You were B1, weren't you?
Yes.
Okay, you remember. It's very nice you remember. Of course, the center, but Diana was B3, so we are still we are right to do this. We are right to do this because for Diana this is new.
Thank
So
you. Appreciated.
Isn't it new for you? Have you seen this before?
No, it's new.
Okay, then that's fine. So you get this kind of behavior. But now I'm asking Diana because Mirel probably knows. Do you think, you know that in general the parameters of systems are not known precisely? They are usually sensitive to all sorts of variations. So do you think this is a stable behavior? The behavior, I'm not talking about the trajectory or the equilibrium. Do you think this center can be held in time when the parameters vary? Diana.
Not really.
Not really. And what do you think it happens if you have variations of the parameters? Because sigma is not necessarily zero, you know? Maybe sigma is something like 0.00 something, true?
Yeah.
So it's usually going to a focus. It never stays like this. It can go to a focus. It can, if sigma is approximately, because sigma can be approximately 0.00 something, or sigma can be minus 0.0001. So it can be either stable or unstable. So essentially, when you get a center, it means that the trajectories, so center means that the trajectories are both so this is x1 versus time, this is x2 versus time. So that means that the trajectories are both oscillating constantly in time. They're both oscillating constantly in time. However, okay, however, if sigma is not precisely known to be zero, you can easily get this, or you can easily get this. Okay, so that's what it means. That's what it means. So this is, we call this, and we are going to discuss this, this is called structurally unstable, because the structure of the center is not stable, okay, is not stable. That's why for a linear system, it's usually very difficult to build a linear oscillator, because if there are parameter uncertainties, the oscillator can have damped oscillations or amplified oscillations, and this is not desired. That's why in electronics, if you want to build an electronical oscillator, you build a nonlinear electronic oscillator, because we'll see that a nonlinear electronic oscillator has a stable oscillating structure. So the structure is not affected by disturbances. Okay? Is not affected by disturbances. All right. Okay, I think that's quite kind of enough for today. I'm going to give you some exercises. You can read in advance. You don't need to wait for me to present you something. You can just anticipate and read more, because you're not in the bachelor studies any longer. You're in master studies, so you do research, and this is a research master. So you can read in advance. I'm going to ask you to solve some exercises, and I'm going to make an assignment for you. I don't think it's very difficult. Of course, we are going to study the equilibria of the pendulum next week, and we are going to discuss more about these things. Probably we'll get more customers to attend the lecture, right? I don't know what happened this week. Probably you were very busy at work and you didn't have time to join. Okay. Questions, please. Diana, especially you, because Mirel is kind of familiar with these things.
I don't have any questions.
Okay. Did you understand anything? Was it kind of clear?
Yeah, it is.
Okay. Good to hear. So guys, you've got files in Maple. You can just install and open and run the files. You don't need to learn how to build them, because they are going to make you nice paintings. And I'm going to ask you for an assignment to do some exercises to find the type of equilibria in MATLAB by numerically integrating the equations and by plotting the phase plane. And then you just have to make comments. This is a saddle point. This is that. This is this, because it has the eigenvalues like this and that. Okay? Do I make myself clear? Okay.
Amen.
Anything else I can do for you?
Nope.
No. Fine. I'll see you next week. Just leave the call open for a while. Maybe someone else will join. Leave it open until 8:30. Just leave the call hanging. If someone else joins and tells us something, I can come back and say more. Okay?
Okay.
Okay, fine. Thank you. I'll see you next week. Hope you come next week.
Yes, we will.
Okay, thanks a lot. Okay, so I leave the call open. I just need to mute the mic.